Okay, so thank you very much for having me. Petter, Nina, thank you for inviting me. It's a real privilege to be here and speak to you about some stuff that Petter and I have been thinking about in terms of applying deep learning models at high frequency and trying to understand the practical challenges around this. Okay, so I'm going to talk to you a little bit about some introduction, some motivation, how we came to this problem. I'm going to define what we mean by return forecasting. I'm going to describe some of the data that we used, trying to spend most of my time on the results, and then I have a few kind of conclusions and other thoughts which I'll collect at the end. Okay, so I'm going to focus today on systematic trading in US equities at high frequency. So if you work at either a hedge fund or you work at a bank, then you're going to be spending a lot of your time doing alpha signal research, and this is very important for different reasons depending on the role that you do. If you work at a bank, you're probably working on building equity trading algos, and if you want these to work well, then you need to have good return predictors. Conversely, if you work at a hedge fund, then you're probably going to try and trade these signals yourself directly. And so in either case, it's very, very important. And for most of these firms, what they really like to do, and what they don't usually do today, is they want to take a raw limit order book or collections of order book if you work in a multi-venue market like the US, and they want to convert just this raw data series directly into price or return forecasts. Okay. And as was alluded to in our introduction, this kind of problem is really very, very difficult. And there are a number of reasons that this is difficult. Venues like the US equity markets generate enormous amounts of data. So you're going to need, you're going to have terabytes or petabytes of data that you need to be dealing with, and then to process this, you're going to need specialist infrastructure. You're going to have to store this. You're going to have to process this. You're going to analyze this, and things like Python are probably not going to cut it for what you need to do. So you're going to have to go and use things like KDB and one tick, and this is complicated. You're going to need a large servers, et cetera, et cetera. Once you've solved this problem, unfortunately, your woes don't end there, in the sense that this data is very noisy, it's non-stationary, it's fat-tailed. So you need specialist techniques to handle this. You need to think very thoughtfully about how you pre-process and build models on this kind of data. And then you realize that this field is extremely competitive. Every single one of your competitors is doing the same thing, and if you're new, then they've been doing it for 10 years before you started, so that this is not an easy problem at all. And so commonly how this works is that these firms employ quants, and these quants spend time extracting and handcrafting features, and they then learn this domain, the peculiarities of this domain. This gets integrated in terms of domain knowledge, and it becomes high-value IP. People move around, the IP goes with them, and this process repeats itself over and over again, trying to extract more and more data from more and more value from the same data set. Okay, but this is somehow kind of not great, and this quote by Rich Sutton kind of alludes to it, and he says that the biggest lesson that can be read from 70 years of AI research is that general methods that leverage computation are ultimately the most effective, and by a large margin. And the ultimate reason for this is Moore's law, or rather its generalization of continued exponentially falling cost per unit of computation. And the most important bit that he says is researchers seek to leverage their human knowledge of the domain to improve performance, but the only thing that really matters in the long run is the leveraging of computation, being able to apply large amounts of computation to this. And these two need not run counter to one another, but in practice they tend to. So if we go back to where we were before, this current state of the art is really this. It is trying to apply domain knowledge and so on and so on. So I guess the question then becomes well, how do we apply computation to this, or how do we start to think about applying computation to this? And I should add here that this is well known to almost all practitioners, so it's not a question of we don't know that this is a problem. The question is more, well, how do we think about this, and how do we start wrapping our heads around this and doing this? So before we get into that in some more detail, I brought some kind of summary slides. So for those of you who are not too familiar with limit order books, we've got one here on the screen, and the yellow is the ask side, and the blue is the bid side, and the gap between the best asked and the best bid is the bid-ask spread. And if you place market orders, then they come and they cross the spread, and if you place limit orders, they post it in the book, and the system evolves over time. And of course, if you have a multi-venue market, then there's lots of these order books, and this is very, very complicated. Okay, so what are we trying to do here? So we are looking at the top 10 non-zero levels of the limit order book, and we are building this vector of length 40, which contains ask prices, volumes at the ask, bid prices and volumes at the bid, and we have the top 10 levels of these, and we want to do a kind of time series regression problem. We want to forecast forward returns, and we want to forecast them in terms of lagged order book states. And these, we're going to use neural networks to do this, and we're going to use a horizon of length 100. Okay, so we're not the first people to think about applying neural networks to limit order book data, and so let me give you a little highlight of what's been done before. There are three main groups of authors who've been working on this problem. You have Santakidis and co-authors. This is a collection of people in Finland. They have been working on 5 Finnish stocks, and they've been investigating different architectures and trying to kind of answer the practitioner question that says, what kind of architecture should I choose if I'm looking at data like this? For those who are interested in this problem, I can strongly recommend the FI 2010 dataset. You can download this for free, and it has several days of limit order book data. It's very manageable. You can do this on a laptop. You don't need any hardware or anything like that. And so this is a nice place to get started for those of you who are interested in this. Then we have Sirignano and co-author. This is the first real large-scale study of limit order books. And he was looking at the S&P 500. He was focusing on a single architecture, a deep LSTM. And he was answering questions of universality. So he was answering questions like, okay, if I fit a model on Apple, and then I try this model on Microsoft, is this good, is this bad? You know, questions of this nature. And finally, there's a group of authors at Oxford who have really done a lot of work in this area, and they've been really focusing on a small number of stocks at the LSE, and they've been really looking at very sophisticated convolutional networks on top of LSTM, using things like inception and using new hardware, IPUs, as well as like sequence-to-sequence models to try and, you know, forecast forward horizons. And that's really what I want to talk to you about today. But despite all of the work here, there's still a number of practitioner questions that I kind of think are important and that we should spend some time thinking about. So should we be transforming limit order books before we put them into a neural network? What about recommendations for practitioners when choosing between different types of architectures? More than that, can I look at model predictive performance in terms of stock characteristics and microstructural properties? And finally, if I do predictions of this nature, what kind of horizons do the alphas that come out of this have? Okay, so we want to recast our problem as standard regression, and we want to include multiple horizons in the output. So we want to try and forecast a time series of forward returns. So I guess you want to think of this as like, let's say I have a trading algorithm and I want to decide, should I be crossing spread or should I be placing limit orders? You'd like to know what the price is going to do some period into the future, and so that's sort of the rationale behind that. And then we refer to these kind of forecasts as an alpha term structure. And so now we want to forecast this alpha term structure in terms of the lagged order book states. And we want to understand, you know, how sensitive is this kind of regression to different right-hand sides? What about multiple architectures across a large set of symbols? And what about relationships between stock characteristics and model predictive power? Okay, so for our study, we used data between January 1st, 2019 and January 31st, 2020. We used Lobster to get our tick data, and for those of you who have access to this is a fantastic resource, and it's great. I have only good things to say about this. To get our reference data information like stock universe, we use Words to collect 115 stocks from the NASDAQ. And now when we talk about forecasting forward returns, it's important to remember that what we're interested in is comparing models cross-sectionally, and the number of updates is not constant across stocks. You have things like eBay, which has a relatively few number of updates per day, and then you have something like Microsoft or Apple, which has millions of updates a day. And so the way we do this is we convert forward horizons into multiples of an average price change. So you take the number of milliseconds in a trading day, and you take the number of non-zero tick-by-tick mid-price returns, and you create a unit that we call delta t, and then we look at multiples of delta t for the forecasting so that when we compare stocks, we can compare them in a kind of fair and unbiased way. And to make this realistic, because we're looking at very high frequency data, we insert a fixed latency buffer of 10 milliseconds. So when we talk about one average price change forward or two average price changes forward, we're really talking about t now plus 10 milliseconds to one average price change, or two average price changes. And this is the kind of thing that people would do in production, because if you don't do this, then you typically see inflated results. Okay, so we looked at a number of different models when we were working on this. We looked at ARX, which is an autoregressive model with exogenous features. This is effectively a linear model. We looked at an MLP, a multi-layer perceptron. This was shown by a recent study by some authors in London to be the best for the problem that they looked at when they focused on Intel. We looked at a simple LSTM. We looked at an LSTM going into an MLP. We looked at like a deep LSTM, which was the model of condenseric nano from the literature. And then we looked at this very sophisticated convolutional LSTM model, which is proposed by the authors from Oxford. So we're going to do a number of experiments, and this slide kind of collects together the experiments. So we have two different types of inputs. We're going to use order flow inputs, or we're going to use LOB inputs, raw limit order book inputs. And then we're going to look at these six different models, and then we're just going to try and understand what we can learn about this problem by looking at different models on data. And you can see here the number of layers, number of parameters. I guess it's important to say that we found a small learning rate was good for this problem, but I think you can probably increase the learning rate a little bit from here. We focused on a relatively small batch size. I think this problem's very sensitive to batch size, so I don't think there's a lot of flexibility here. And we used 50 epochs because that was just a number which worked out kind of well for training. Okay, so when we do these model fits, we wanted to kind of mimic how people would do this in practice. So we want to do these kind of rolling fits where you look at some history and then you roll the whole thing forward and you do this process continually. So we choose what we call 1-4-1. So the first week is for validation, which is for the early stopping. The middle 4 weeks are for training, and the final week is for out-of-sample testing. We did some Windsorization and some Z-scoring to the independent and dependent variables, which help with cleaning up some outliers. And then we use the Atom Optimizer and TensorFlow. And of course, this is fairly time-consuming, so we use the GPUs on the NYU high-performance cluster, which is the Green and Hudson. Okay, so we used out-of-sample R-squared as the evaluation metric, which we calculated daily for each model, stock, horizon, and out-of-sample data. There are definitely other methods. We wanted to ask a question about statistical fitting. So can you statistically fit returns rather than, like, can you trade these or can you turn this into a trading strategy? A lot of people are interested in this, and I'll try and speak to this a bit later on. But first question we wanted to ask is there signal in this that you can actually extract and fit? So the first thing we wanted to do is look at the horizon. So we take our out-of-sample sort of array, and then we average over stocks and dates. And this gives us a curve across horizons for each model. And that can sound a little confusing, so like the picture is just a bit easier to see. Okay, so on the left, we have what happens if you use order flow inputs. And on the right, we have what happens if you use raw limit order book inputs. We have your 6 models in different colors. The y-axis gives you the out-of-sample R-squared, and the x-axis measures the fraction of an average price change that we're looking at. So we look between 0 and 2, and then in the paper you can find plots right out to 10 average price changes. This is, I think, the most interesting region to look at. And there are sort of 3 interesting conclusions that I would take away from this plot. The first is that by looking at the scales on the left and right, you can see that order flow inputs are a significant improvement over raw limit order book. So the fact that you have stationary inputs seems to make a big difference to the problem. And this is, sort of to digress a little, this is what drew Petter and I into this problem, was that if you look at raw limit order books, the econometric literature will tell you that a lot of these inputs are not stationary at all, and that you wouldn't normally do a linear regression of non-stationary right-hand side against stationary left-hand side. And so we wondered whether you should do this here, and that's kind of how we came here. So differencing makes a huge difference to the output. Second of all is that the lines group themselves nicely into groups. You know, the red and the green go together nicely, and then the blues and the yellows and the purples all go together nicely. And what's the difference here is that these blues and purples and yellows, these all have an LSTM in their architecture. so that having some kind of sequential time series model makes a massive difference. It doesn't matter so much what you do with it. Like, if you look on the left-hand side, you know, whether you have it be a deep LSTM, which is the purple, whether you have it be a complicated convolutional structure on top of the LSTM, it really doesn't make a ton of difference. Once you put an LSTM model in there, you get most of the gain. So you can get a lot of the gain here from just doing some simple differencing and putting into some well-known established neural networks. Okay. So if you think about the key questions that we kind of set out to address here, we wanted to understand the effects of different right-hand sides in the regression, and we wanted to compare multiple architectures across a large set of symbols. So we did that, and we concluded that the order flow input is much better than the limit order book input, so stationarity is very important. We found that LSTM-based models outperform non-LSTM-based models. We found that the depth and the convolutional layers do not seem to outperform plain LSTM after you convert to order flow. And if you read the paper, you can see all the statistical testing where you find that we have significant alpha at all horizons. And although the R-squared is small, you have potentially high profitability because you can do a lot of trades. You have a small amount of edge, and this is multiples of a price change, so you can have lots of these a day. So you can maybe do plenty of trades, and you can probably build something profitable from this. Okay, so that was the first thing that we were interested in. And the second is to say, well, what about stock characteristics? You know, how can I understand whether these models are going to be good or bad? Okay. And so what we did is we fixed our input as an LSTM model with order flow input, and then we looked at 4 main microstructural characteristics: tick size, log number of updates, log number of trades, log number of price changes, and all of these were computed by averaging across the time period. And so what we did is we basically did a scatter plot. So each point here is the average for a single stock across all the horizons for that given model. And the top left is the dependence on tick size. And you can see that we clearly have an increasing relationship on tick size. Same is true for updates, but the relationship is a little bit weaker. It's sort of similar for trades, but a bit weaker still. And then for price changes, it's all a little bit noisy. But in any case, you do have clear dependencies on updates, tick sizes, and trades. And you can see a regression analysis, which you can use to combine these to get the best explanatory power. And so you may ask yourself, why is this the case? Well, when you have log updates over price changes being large, you have a very stable order book. So you've got lots of updates as per price change, a property of large tick stocks, and you find that you can have data and complicated patterns forming between time series of imbalances and price changes, and the LSTM model is able to capture and model this. Also, there's lots of evidence in the market microstructure literature that generally it's easier to build alphas for large tick stocks, and that's sort of what you're seeing here. And anyway, we have good out-of-sample performance across the vast proportion of our universe. And this is the final graph to show you that we do a reasonable job explaining performance in terms of microstructure characteristics. And if you're interested in this, you know, there's many more questions and sanity checks and stuff in the paper, and I would encourage you to read it. So things like how far ahead can we predict returns? It's about 2 to 3 average price changes. How sensitive are the results to the fixed window length? Interestingly, not very. You know, what happens if we use order flow imbalance rather than raw order flows or volumes? It kind of helps a bit, but order flow is definitely the best. And we provide some motivation for these results in terms of inductive biases, which is a new kind of concept from the machine learning literature. And ultimately, what this says is that limit order books are a sequential system. And so models like an MLP have no notion of order or sequence. And so this is probably why you're getting a lot of joy out of your LSTM, because this is fundamentally a sequence model. Limit order books are fundamentally a sequence object, and these two are combining to give you good kind of predictions. So I have a few conclusions. We built some framework to evaluate these different regression inputs and deep learning architectures. We showed that stationarity was super important. We showed you that predictive power depends on microstructural properties, similar to what other people have found. And we kind of suggest that actually we need more evidence, we need to spend a bit more time focusing on best architecture for return predictions, as we're not really able to get as much joy out of the complicated ones as one would hope. Okay, here's a few references, and that's all I have for you. So thank you very much for
Thank you very much, Nick. And we have time for some questions before the next speaker. Do we have any? Fabrizio? Yeah.
Point returns, mid-to-mid returns. Yes.
But of course you cannot trade at the mean.
No, you can't. So this is, as I said
So,
to you
so the
before,
question was, are you forecasting a return, or are you forecasting a mid-price? And the answer was mid-price. Nick, go ahead.
Yeah, so this is a fantastic question. So let me answer this and then give you some more color. So first of all, we want to understand if there's predictability in the mid-to-mid returns. After this, you start to get to questions of like, how would I trade this and things like this? And you get into subtle questions of like limit order placement and market order placement or some kind of market impact model. And I think the right approach here and the way we'll think about this is we will probably understand how good would an execution algorithm need to be in terms of spread capture for this to be profitable. I think that's probably the way we would consider this or think about it in this way. Before just jumping straight into when you try and build trading strategies, you have questions like, how long's the holding period? What's the size going to be? And what's the execution style going to be? Which complicate what is already quite a difficult question in terms of, is there any predictability? So I think we're coming at from the point of view of like, if is there predictability, which it seems like there is, then the question is, how much would be left once you assume some reasonable model for execution? And if there's something left over, then you start from at least firm ground where you know the thing I have actually has some predictive power, and I'm not trying to like fish through all the parameters of a strategy to like make it work. But this is a great question. Thank you.
Thank you for that. Other questions? We have a little bit of time here, so since there's no other question, let me just ask a question to my collaborator here and put him on the ringer. No, maybe you can speak a little bit to where you alluded to where this can go next, but maybe share with us a little bit your thinking around, well, what about some of the other type of architectures that people are looking at, maybe sequence-to-sequence models, transformer-based models, and so forth. Would that be helpful here?
Yes, this is a very, very complicated question. So I have explored this a little bit, not in great detail. My feeling is that the direction where there's a lot of focus on bringing NLP-based architectures into these kinds of problems is not necessarily the best path to go. Like, it's not clear to me at all at this point that limit order book data is the same as like neurotranslation, which is where a lot of these models are used. Like neurotranslation or sentence-to-sentence kind of translation, you're taking typically like one idea in a sentence and you're converting that into an idea in a different language. It's not clear to me that you can think of an order book in that way, that you can think of an order book as conveying a single clear like concept or idea that then can then be understood in terms of returns. And so it's not clear to me that this is the right way, sort of conceptually speaking. Also computationally, the sequence-to-sequence models, you need the powerful, like even more better accelerators than GPUs, you need IPUs and things like this. And yes, it's not clear to me that this is the path forward at this point. Great,
thank you very much for this, Nick. Let's give another round of applause.